So we're doing acids and bases, part 2. This is that first page with all the notes. And so we're going to talk about some reactions today. And when we go over the study set, when I go over the study set later, there's some reactions on there. So we'll see more practice of the reactions. So when you write the reactions, you're labeling the acid and base, looking for one of the, if you see one of the strong acids like H2SO4, HI, that's a wonderful thing because it's then a one-way reaction. And then you only change by one hydrogen. That's the key. The acid becomes the conjugate base, the base becomes the conjugate acid. And then we do which direction is favored. This is the key, and this makes sense. That this is part why I have you do the study set, that split the study set into 2, because by you trying the study set before this lecture, you're probably paying more attention because you're like, I missed some key things somewhere in there. But the stronger is always pushing the reaction. So whichever side has, if you have a strong acid, it's one way. If you don't see a strong acid, then we look for hydronium or hydroxide, which happened in these middle, in B and C. So E is a situation, E is a tough question. So couple things are happening in this one. One, sodium shows up, and we're going to talk about ions today and how they impact pH, but sodium doesn't affect pH at all. Sodium ion, it is neutral to pH. So you can always just cross it out, as I mentioned, and when you cross it out, you just then put a negative, or you can keep it there. I'm going to show you both ways. Now, the issue we have with this one is more in the sodium. Sodium's the easy part to resolve. Both of these are amphiprotic. That would have been a good bonus question. I should have asked that. They both have a hydrogen, and they both had a place where you could have had a hydrogen. You can replace the sodium with a hydrogen. So the amphiprotic means either one could be the acid or base. So you don't flip a coin. I mean, you could if you were desperate. Remember at the end of these notes, there's those charts that I alluded to yesterday. We go to those charts and we find these on the chart. So I saved this problem and I wrote this problem to talk about the chart. There's 2 different charts. So the one chart is alphabetical order. So like on the study set, there's one where it's oxalic acid. So it's really nice. You just find the word and then you look over. This one, oxalic acid, has 2 hydrogens. And so it has 2 different K values. We're going to go with the first K value. At some point, I do talk about the second K value. That will either be today or next week. I don't remember where it shows up. We're going to use this chart that's on page 18. It actually comes from the textbook that we always used. That is like the best textbook, except the books all became like $300-400 books, and they priced themselves out of business. So this chart, I like this chart better because what it shows is from strongest. The acids are listed all on the left side of the chart, and it goes from strong to weakest. And these are the acids. And so then it gives you the formula of the acid and the name, because sometimes I give you the name, sometimes I give you the formula. And then it gives you Ka values. And these first 4, it just says large. And that is because those are 4 of the strong acids. So HClO4, HCl, HNO3. So that's why. So those first 4 don't get a Ka value because they're one way. They're just outrageously huge because we just treat them as one way. If you notice what's next, it's hydronium. So hydronium and hydroxide, they're the cusp of where things, where the change happens. All right, and then it goes from there, from strong to weak. And we're going to do some problems with that because reading these Ka tables and comparing Ka values, My guess is that half of this class is going to be taking organic chemistry in their future. And that's the very first 2 weeks of organic chemistry. In fact, some schools, the very first day, they give you a quiz. And if you don't pass the quiz, they kick you out of the class. They just delete you from the class. And the quiz is about KAs, which is really fascinating. And so then I'll often get a thank you note from a student who's like, yeah, so guess what? I just had that quiz on KAs. Thank you. It was really simple. The other thing, while we're looking at this chart, is it then shows the base, which, so if this is the acid, this is technically the conjugate base. And there's going to be a little thing you're going to keep hearing me say this mantra over the next week, because we keep doing this. The stronger the acid equals a weaker conjugate base. Because they're a pair, the stronger the one is, the weaker the other is. So if the acid strength becomes weaker as we go down, what's happening to the conjugate base strength as we go down?
They're stronger.
Yeah, so we're starting at weak and we're becoming stronger. And so then with this last column, or second to last column over here is the KB. Those KBs are for the conjugate base. And you can see the values of KAs and KBs are less than 1 because they're not very favorable, right? Ks are less than 1 are really, they don't like to ionize at all. And you can see the Ka values are getting more and more negative exponents. So they're becoming much smaller until they get to the point where I don't consider them even Ka values at all because they're too small. And if you look here, the Kbs are actually getting bigger corresponding. I mentioned yesterday there's 6 strong bases. These are actually some of the strong bases over here, but we're not going to work with those. But in case somebody is always curious about that, there's classically 6 strong bases. There is something that shows up down here that I'm going to point out since I noticed it and somebody would notice. Ammonia is here, and we talked about ammonia yesterday. Ammonia, it can't act as an acid. Here it's in the acid column and it doesn't even get a Ka value, because what happens if it acts as an acid, it would have to give up a hydrogen and become this, NH2 negative. And I'm pretty sure none of you have ever seen that. I've never seen it except in like a random question. I don't ask that question. NH2 negative is extremely strong base. It's like because it doesn't make sense. It wants to be NH3. And so it's going to be highly reactive, highly dangerous to work with and stuff. And so it's a man-made compound is my guess, because it's useful industrially to make things happen. All right, so back to the question we're working on. We have to find those 2 that we're talking about, which is the H2PO4 and the HCO3. So we have to find them as acids to figure out which one's the acid. So whichever one's higher up. And so here's the H2PO4 right there. So the Ka, I'm just going to write the Ka underneath on this page is 6.2 e to negative 8. And the bicarbonate is down here. It's lower down, so it's weaker. The Ka is 4.8 e to negative 11. So your teacher has looked at this chart enough. I know what I'm looking for. And so anyway, that's the idea of the chart. What you're going to see is I'm going to give you mini charts like on the midterm or something, and it's going to have maybe 5 things on it. And we'll see a question like that later. So you probably won't have to use this whole chart, but do know it's there in case you run into a study set or a worksheet question. And we're going to need to use the chart I gave you if I don't give you Ka values, so that we all have the same Ka value. Kas and Kbs are very approximate. Every chart gives different numbers. And so that's why I had to learn how to scan the chart in so that we all had the same chart. All right, so let's go back to this problem. That's the idea of the chart. We'll come back to it in a little bit. All right, since they're both amphiprotic, we have to decide which one is the acid. and it's whichever one has the larger Ka. So this is the H2PO4 is my acid because it has the higher Ka. That would mean this guy, we're going to ignore its Ka. This must be the base. So again, your reactants are the acid and the base. You can't have an acid plus an acid. They're not going to react that way. This is again where I like to, and I've seen the students who do this little simple thing where you circle the hydrogen and you move it over, tend to do it a little bit better, especially if it's more complicated. My question for you is, do I do 1 or 2 arrows? And why?
1 arrow.
2. We're going to do 2. When do we do 1 arrow?
When it's
a
acid.
strong acid.
When it's a strong acid. And these are not one of the 6 strong. So yesterday, and I forgot to put it on the board behind me, but these are what we're going with as our 6 strong acids. And again, some books will now say, I think your free textbook says HClO3. I just try to avoid that question so we don't run into that dilemma. All right, so this is now going to be HPO4. So it loses just 1 hydrogen. And now it's going to have a -2. So if you took the sodium away, it had a -1, and now it lost 1 hydrogen, so it's a -2. The acid becomes the conjugate base. And this is going to become H2CO3. I'm smiling because there's a lot that happens on this question. Like we should have just done a whole page on this. This could be like your whole exam, is to just see if you can do this question and explain all the bits and pieces. So this is called the conjugate acid. All right. If you wanted to do the sodiums, like you're like, no, I want the sodiums in there, I don't want to cross them out, where would the sodiums be on the product side? There's 2 of them. It would both be here because this has the -2. So the sodiums always move. The sodium and the hydrogen switch places. So since the hydrogen went over here, the sodium would come over here. So if you want to show the sodium, you would have Na2HPO4, and then you would have no charge. The bicarbonate, when it picked up a hydrogen, it loses its charge. So there's one more piece, but questions up to that point. This is a tough question. This piece, though, is actually important. H2CO3 is unstable. It's rather emotional. And whenever it is your product, it decomposes. So you can never actually make H2CO3. I show it in the reaction, and does anybody remember back to their first term in chemistry? This is going to decompose into 2 things.
Water and gas.
Yeah, so what I like to do is show it as H2CO3. Now, if you're given it as a reactant, go ahead and react it normal. It's if you run into it as a product. And so think of, we like water, right? Water is the basis of our body and of the planet. So if you pull out the H2O, so the 2 hydrogens and the oxygen, you're left with CO2. And that makes sense. This is what's going on in our body. So we can balance the pH in our body with our breath, because we can change how much CO2 we have. And so the CO2, the rate that we're breathing can change the pH of our blood. That's next week's lab we're going to talk about. I have to finish making that video. All right,
So
there's
would
one.
we write that instead of writing H2CO3? Would you want H2O? So like HPO4 plus H2O plus CO2. Would you expect us to know that? Yeah.
So Perry, everything's going to be show your work. So let's say this was a question on the midterm. You would lose 1 point. You would get part credit because you had it there, but you forgot to change it to the H2O and CO2. Now, with that, what she said is you can write it like some students have it. They never even write the H2CO3. I personally like I write it and then I cross it out and write above it H2O and CO2. That's like a personal preference. I don't care which way you do it. So you can do it how I did it, or you can just like not show the H2CO3 at all. The other question that comes up with it is if you don't show which one's the conjugate acid. In all honesty, I don't really care. Both of them are a conjugate acid. So you can label either one. You're kind of putting them together there. Now we're going to predict which way this reaction goes. And to do that, we don't have a strong acid anywhere in this equation. We don't see the hydronium or the hydroxide. So we have to do step 3, which is look at the Ka. And you look at the Ka of the acid versus the conjugate acid. So the acid's on the reactant side. We already looked up its Ka. And now we have to look at the Ka of the H2CO3. So we can go back to that chart. And you're looking at Kas, not Kbs. So it's easier to just always compare Kas. You could also do the same thing by comparing the Kb of the base and the conjugate base. So it's H2CO3, kind of back to what Perry had just asked. In the chart, it's going to show it as H2CO3. So we just respect that, and it should end up higher. It's right here. So it's 4.2 e to the negative 7. You can also Google it, and because we're not doing the math here, we're just getting approximates, and they're going to be approximately similar. That's like, you can quote me on that, approximately similar. All right, so take a deep breath. Which of these numbers is larger? 4.2 e to negative 7 or 6.2 e to negative 8? I'm giggling because I know which one's larger. I don't have a problem with exponents.
4.2 e to the negative 7.
Yeah, so some of you, this is your struggle your whole life, and it's because you learned about negative exponents at puberty, and that's like, they should really, I grew up in the East Coast, and I learned about negative exponents like in 6th grade or something, I think. So this is stronger. It's not strong, it's stronger. It has a higher Ka, so it favors, we're going to favor the reverse reaction. I'm so missing having big chalkboards where I can just write all over. All right, a lot of information in that question.
Sorry, I had one question. So when we look at the
it.
Ka, we look at the Ka of the conjugate acid.
Yes.
We don't look at the base at all. Okay.
No, we would then you'd be comparing Kb. So Kas go with acid, things that are labeled acid. So in our reaction, this is my acid, this is my acid. So you're looking at that. These are bases now. In this reaction, they're acting as bases. So they don't, even though they could have a Ka value, they don't for this reaction. The other quick comment we're assuming is that it's a closed-ish system, so the CO2 is not escaping. So I'm torturing some of you like Paul, who said you like just keep going in your analysis. So don't do that. Just look at the Kas. It's going to go reverse. All right, let's go ahead and finish this page. These are actually things that you kind of learned back in 221 in your first term, but we're looking at it in terms of acid bases. In the good old days when we did a standardized final, this was like big on the standardized final. This was like 4 of the questions. And I have no idea why the American Chemical Society thought this was such an important thing, but this is not ions. So kind of make a note, these are not ions. We're going to deal with that in 2 pages. This is a true metal, like magnesium. See how it's a solid there? If you take a metal and you put it into hydrochloric, if you add an acid, you're going to get a reaction. The acid's going to eat away at the metal, right? You're going to get a reaction. This is when we did it in 221, we called them single replacement, or it's an oxidation reduction reaction. So the magnesium is going to, and if we actually come back to this when we do oxidation reduction again. So the magnesium and the hydrogen are going to switch places. This is a one-way reaction for a rate. And so we're going to get magnesium chloride. The magnesium goes to a +2 charge. You all remember that from your periodic table, right? Magnesium. You have put your periodic table back up there somewhere. And what's my other product going to be?
H2.
Hydrogen gas. So the hydrogen is going to be bubbles of gas are going to come off. We would actually technically have to balance this. So we would have to put a 2 in front of the HCl. So anytime any metal is going to be, you can do an exchange reaction. Now with that, when we get into oxidation reduction, we're going to see another one of these charts and we'll refine that. So the rule here is, well, that's it. That's just kind of, it's the next one that I wanted to talk about, G and H. I'm sorry, G and I. If you took a metal, so in this case, I took sodium, right? So in nature, the reaction happened already. So you're already over here. You're not going to find sodium and magnesium as metals. But if you took sodium and you put it into water, you get an explosion, right? So some of you did sodium as your paper, your presentation and stuff. Good time to remind you, it's Thursday, so ideally, I would love for you by Monday, if you haven't already, to have like looked into a famous chemist and stuff. I become more persistent next week. All right, so it is an exchange reaction, the same idea. The key with water, if you didn't get this, is water is not 2 hydrogens and an oxygen. Water is a hydrogen and a hydroxide. So what's going to happen is the sodium wants to be sodium ion with a +1. And so it's going to form sodium hydroxide and hydrogen gas again. You can balance by doing 2, 2, 2, 1, or you could put a 1/2 in front of the hydrogen. I don't really care if you use fractions to balance. So the general rule is metals, when you place them in water, they form a basic solution. So what are the 1As and the 2As called? They have a family name. The 1As have one name. Anybody remember?
Earth metal.
Alkali
Alkaline earth
metals
metals.
and alkaline earth metals. So they are called that because they knew our common bases, what we eventually called bases, came from those, that sodium hydroxide, potassium hydroxide, calcium hydroxide. All right. So in nature, they already had formed the hydroxides. If we skip down to, this would just be, we're not going to worry about, let's just not worry about H for now. Let's skip to I. So if we're on the other side of the periodic table, if you take a non-metal in water, this would be the same idea. The metal oxide or the metal in water is going to form a basic. A non-metal is going to form an acidic solution. So it's kind of the whole idea of yin and yang. So we're on the left, metal versus non-metal, acid versus base. The key here, though, is we're dealing with them as elements, not as ions. So non-metals, you're not going to really find them by themselves. You're going to find them as a compound with the oxygen. So like NO2, CO2, SO2. And so NO2 plus water, you're going to end up with HNO3. More than likely, I'm not balanced. I have to think too hard to balance. Let's just leave it like that for now. That's where the whole acid rain thing comes from. is the nitrogen oxides and the sulfur oxides combined with water, and you end up with an acid. So sulfuric acid, sulfurous acid, nitric acid, nitrous acid. And I apologize, I can't figure out where my balancing. It must be that you get hydrogen gas. Let's just do that. Sure. So we'll do the 1/2 hydrogen gas. That gives it balanced. When in doubt, go with a diatomic, right? All right. The lab for next week, which I'll open the folder for next week, ideally after class today. Next Friday's lab, the lab that's due next Friday is a kitchen chemistry lab, so it's cabbage juice and stuff, but there's a video that goes along with it, like a 20-minute video, and I have a little bit about acid rain in that, so we'll just move on. But it is that the pH of the rainwater in industrialized areas has decreased. So if you want to go see the Taj Mahal, well, you can't go to India right now, but maybe in a couple months or a year. The East Coast has a much bigger issue because it's more industrialized than we are here. So Ohio, if you ever take a train through Ohio, you will know what I mean. There's so much industry there that there's so much sulfur oxides and nitrous oxides released that the pH of the rain has changed. All right. Let's see. And Europe actually has a huge problem with that. So that's the chemical equations. And when I go through the study set today, the first, trying those questions, the worksheet might be easier than the study set. But right, all right, pH. We talked about this page, and there's a whole bunch of formulas. So always state your formula. A lot of the questions, there's going to be more than one way to get to the answer, but this would be where if I had a highlighter. So hydronium and hydroxide will always give us 10 to negative 14. You can also get around with pH plus POH is always going to give you 14. I like this formula better, but you can also use this one. And then, of course, anytime you see the little p, that means negative log. So POH is negative log of the OH. And the way you get rid of it, if you're given the pH or the POH, is you do 10 to the power. And this is going to be something we use for the next 2 weeks. And so it just becomes ingrained in you with how to get around with logs and pHs. All right. So this was the page that we were on. Most substances are weak acids or weak bases. So when I'm solving it, I use this formula. I prefer this formula over how a lot of other people teach it, just because it allows us to do it in different ways. So at this point, for study set 3, study set 4, for the first celebration, these two pieces in the numerator are going to be the same. So if you're dealing with only an acid present, it means we haven't done a mix. We haven't started to titrate. We haven't made a buffer. So you only have an acid present in the water, then you have an equal amount of, it's going to ionize to an equal amount of these. And so that means we don't have to do the whole ice table and stuff. Next week after the midterm, there's a couple of you who have already anticipated, we get into buffers and titrations, and we'll worry about that then. So for now, this makes these wonderful problems that the two pieces on top are going to be the same. So we call them x squared. And also, we're going to always make this assumption that the x is going to be so small that we can ignore the subtraction step. That's going to be true with the weak acids and weak bases, not with study set 1 and study set 2, the stuff we did with equilibrium where we were making the ice charts, and not when we get to the buffers and the KSPs and things like that. But we'll worry about that then. I wanted to go through C and D just briefly. And I apparently mentioned this, and this shows up on the study set and the worksheet today. You have a question like this. So you either want to number your steps as you're doing it, or make sure I can follow the order of your steps. So first thing we have to do is to be able to use this formula, to be able to use the pH formula, to use any of these formulas that I gave you, you have to be in molarity. I did mention that. All right. So the way I do it is I just start, I do a little factor label thing. And I'm just going to change it grams to moles and milliliters to liters. So last year I commented, oh, you can just move your place value. I had never done that for 25 years. I said, show the step. And it is because students don't move their place value correctly. Even here in this online home environment, people do really weird stuff. So I would actually show the step. And this we would have to add up, sorry, our carbons and our hydrogens. You guys remember how to do that on your periodic table. And I want to point out a couple things. Oh, that is not right. So this should be around 94-ish to 1 mole, and then either 1,000 milliliters to a liter, or some of you who are with me, the way is you can also do a milliliter is 1,000th of a liter. I don't care how you show this step. Just, I recommend you show it so you make sure you get your number right. This is going to give us that capital M molarity. You have to be in molarity. So show your work. This is where, so Perry and Peter and Paul. So since you guys had, so you had different teachers, students who had Bernadette, students who had myself, you guys can do factor label. It's students who come from like the universities or Dr. Russell. Dr. Russell doesn't like factor label. This is a really nice little tool. You saw it. So just put your mass over your volume and then just show it in this nice little, you can do it. I had a student last year who had Dr. Russell, and it was so funny. By like the 3rd week, she was like, she had mastered factor label. She's like, oh my God, I can't believe it. Sorry, I had to punch this in to figure out what my number is. I actually do it a different way than this. And if I get a chance later, I'll show you. I recommend that you keep 3 sig figs, even though, yeah, just let's keep 3 sig figs. Let's go with that rule. With pH, you're going to want, this technically has 2 sig figs because it goes 2 decimal places. But if you round this to 0.017, you're going to end up rounding too much. And it's going to give you different pHs. And that's going to end up being an issue next week. And like already, even on the first worksheets, before we got to pH, some of you are rounding too much. And so I'd rather have you be like the people who are keeping. So keep 3 sig figs at least. The 0 is not significant. It's a placeholder. All right. Our second step, state the formula. It's a weak acid. We know that because the Ka is given. So state your formula when you use it. And again, you can just say acid or you can say weak acid, and then we're going to plug in. So our Ka equals, and these are going to always be the x squared. That has to be molarity. Has to be molarity. That's been like the biggest question. A lot of students are doing moles. It will not work. And then your third step would be that the negative log of your, when you solve for x is going to be your hydronium. So the negative log of x is going to be our pH. And we get 5.83. So this is a pretty weak acid. That's a pretty small number. So our pH is just barely acidic. The pH is below 7, but it's not a very high pH. The way I actually solve it, I do it this step 1. I don't do it as a separate step. I actually do it all here underneath and just leave it all in one setup. And then I find X and do a negative log of that. So that's our idea there. Questions? Oh, and then to find the percent ionization, I didn't ask for it, but that's what that percent is. The percent is the change, or X over initial. So the value you get for X over the initial times 100 will give you the percent. And you can see it's a really small amount has dissociated. All right, times 100, right? All right, on D, it is a Ka. So we'll state our formula. And before you start plugging in, we want to look, this one's a little different. You have one like this, I think on the worksheet. This one we're solving for Ka. The one on the worksheet, I think you're solving for Kb. So the pH, if you're given the pH, we can use that to find the hydronium. So 10 to the negative pH is our hydronium, right? Sorry, I should write that down here. 10 to the negative pH equals my hydronium. That was one of those formulas. So stating the formula. So what I do here is I just write 10 to the negative 2.43. I personally just leave it like that. And I don't really care what that number is. What I have found is about half of you mathematically, you're perfectly fine with that. And about half of you, your brain's like, I cannot handle an exponent that's not a whole number. I don't like that. And so then punch it in your calculator and find what that number is. You're going to square this number. Because these two are the same, because all we have present is the acid. So when it dissociates, you're going to end up, these are the same. So basically, this is my X squared, and then my acid is the 0.10 molar. And we would punch that in. Now, there's one other piece, and this is more for a cup. You can leave it like that. You would get full credit. Technically, there is always a minus X aspect. And so some students, like if you go online, you might be watching videos from somewhere else. They will often show the minus the X aspect, and it doesn't make a big enough difference. So I recommend you just ignore that. So this is my acid amount here. This is 10 to negative pH squared, because that's going to be my hydronium, which is my conjugate base, and that gives us our Ka value. When you do it on the worksheet, be careful because it's a Kb. And so remember, when you're working with Kb, you're working with bases, which means hydroxide. All right, any questions? Today, the worksheet's really not bad. The worksheet might be easier than the study set. Try your best. The study set, the first page of the study set isn't math, it's just thinking. So do something, write notes, and I'm trying to find my next page. That is study set, page 15. All right. So we're going to talk about salts, and then, yeah, we have to get to that page. I did want to mention that I'm planning to have Friday office hours tomorrow. I don't know if somebody has an opinion of what time they want those office hours. Do you want me to just keep the same time?
Morning or 1 p.m.
1 p.m.?
Yeah, it should work.
Okay, let's just say I'll be on at 1 p.m. It's the same link as this one. And so we'll say from 1 to 2, but if there's a lot of questions, I can stay longer. And I might also be having one later if there's people who would prefer to have it later, or you can speak up. You do have a lab due tomorrow. So if you want to come and have me look over your lab, if you didn't get a worksheet done this week, so 1, 2, and 3, and you want to come in and go, or if you turned in the worksheet and you got like a 2 out of 5 and you're like, ooh, I would have written you a little note and said, hey, we can redo this, come to an office hour. And so tomorrow would be a great time. And yeah, you can also, right. All right. And again, I'll be putting the stuff that's there for Monday for next week also. So we're going to talk about salts, which means ions. This is different from when we did our reactions just a moment ago. These were not ions. And so it's going to come out the exact opposite. So just be careful. These were dealing with solids or a gas state. The ions are going to be aqueous. All right, we're limiting ourselves to 3, 4 states of matter, even though there's many more. So there are 3 situations for each one. And most ionic compounds will ionize when you put them into water. Some ions do affect pH and some don't. So for cations are, cats have paws, so positive. This 1A's and the 2A's. So on your periodic table, the first 2 columns. So the alkaline metals and the alkaline earth metals, these guys are neutral, neutral pH as ions. So that's sodium ion, calcium ion, etc. They have no effect on pH. They love to make, right? We talked about that before as the thing. All the others are going to form acids. So that would be the transition. So like iron, aluminum can do this. And that is because they can form complex ions. If you look at the syllabus in 2 weeks, we have a whole lecture about complex ions. Complex ions are complex. They're more than just the iron. So what happens is the iron pulls hydroxide out of the water and you're left with the hydronium. And so that's why they act as acids. So these guys are going to act as acids. So that makes sense. When we write compounds, when we write ionic compounds, we write cation before anion. So the acid part is the first part. There is one other possibility, and it also acts as an acid, and that is the nitrogen when it has that extra hydrogen. So like ammonia, it also acts as an acid. So yeah, because it has extra hydrogen. All right, anions. And I'm just always amazed, as there's certain things when I'm teaching at the board, it just flows, and having to write it, it just like gets stuck in my brain. The anions, so you're going to have some that are neutral, and then all the others are going to be basic. So anions are negative. So sometimes we teach it as onions because they make you cry. Something kind of cool about anions, negative ions are actually the ones before a storm comes. Like we don't get those here. There's more anions. Waterfalls make the air have more anions. And that's why whenever you go by waterfalls, you feel better because our body actually, anions have a healing thing. That's a whole different thing from acid base. But if you've ever heard anything about that, moving water actually, so that's why storms and waterfalls and stuff. The ones that are neutral are the conjugate bases of the strong acids are neutral. And the reason for that is strong acids are one-way reactions. So their conjugate bases can never get back to where they started. So most ions, so if we think of it like F negative has a negative, so it can absolutely bases attract hydrogen, right? They accept hydrogens. And so that negative charge, we think of it as attracting it. So fluoride, it works. It's a base. It's going to attract a hydrogen. But something like Cl negative, it can't attract the hydrogen, because even though it might attract the hydrogen, that would make HCl, and HCl would just immediately push it back because it's a one-way reaction. So Cl negative, Br negative, I negative. So remember these guys, we talked about the 6 strong acids. They can't go back. They can't pick up the hydrogen because it was a one-way reaction, so they can't go back to where they started. There is ways that they can make them, of course, but it's not going to be an acid-base reaction. It has to be a different type of reaction. All right, there is one other situation, because there always is, and we'll use a different color. That is, there are some things that are amphiprotic. And I already alluded to this in that equation that we did. So if you have something, say, we'll actually see it here. So let's do it with this one. So let's say we get HPO4. So let's look at this example here. So the calcium has no effect on pH. So if something has, because it's a 2A. So if it's in the first 2 columns of the periodic table, or it's the conjugate of a strong acid, we ignore it. All right, we're left with HPO4. HPO4, we'd have to look up the Ka and the Kb. We're not looking at its conjugate, we're looking at it itself. It has a hydrogen it can give up, but if we take the calcium away, it has a -2 charge, and that -2 means it's going to attract or accept hydrogens. So we have to go back and find that chart again. And this time when we look at the chart, we have to find the HPO4, which is down here. And that's its Ka value, is HPO4, 3.6 e to the -13. Sorry, I have to find my thing. But I can always tell you that's already like such a small number. That's as the acid, because that's the acid side of the chart. Now we have to go to the other side and find it again and find it as a base. HPO4, not its conjugate, but the actual thing that's given in the question, and it's up here. What's up higher? That must mean something. And so as a base, it's 1.6 e to the -7. So again, you're not looking at its conjugate, you're looking at what I actually gave you. So here and here. And then we compare those 2 values. This is the larger value, so it's going to act as a base. That's the hardest one of these to do. So let's walk through the other ones, or question. Or when we do the studies on Monday, you'll get to do some of these, and that usually refines it. All right, the trick to doing these. First, look for any 1As or 2As and cross them out. Like here, we see potassium, ignore it. Remember on the sodium question? I said just cross the sodium out. And the reason is they don't affect pH. It's only the 1As and 2As that don't affect pH. So those first 2 columns as ions, and they don't form complex ions. Here we see sodium, so we're going to cross it out. The other thing we're going to always cross out are the conjugates of the strong acids. So if you find your chart of the strong acids, ClO4, HClO4 is actually the strongest of them all. And so you cross that out. If you cross out everything, that means it's neutral. So sodium chloride, you would cross out sodium, you would cross out chloride. It's neutral. It has no effect on pH. All right. on this one. The iron, we don't cross out. So the iron's acting as an acid. The Br, we do cross out because it's the conjugate of one of our strong acids. So if you're only left with the acid, it's going to be an acid. Sometimes I do ask it like this, is it an acid, base, or neutral? And sometimes I say, what's the pH going to be? So if it's neutral, you would say pH is 7. If it's an acid, you would just say pH is less than 7. All right, the next one, NH4, that's an acid. So again, I said if you see nitrogen, this though it has a charge, it's a positive charge. NO3, that is one of the conjugates of a strong. So HNO3 is one of the strong acids. I mentioned yesterday to make like a little flashcards of those 6. So you're like, you see it right in front of you. Yeah. Maybe I'll write it up on the board while you try a problem in a moment. So we're only left with the acid. So again, that one's an acid. On the next one, we cross out the sodium because it's a 1A. And NO2, we do not cross out. NO3s we cross out. So our strongs, I should just write them up there. Our strong acids, HCl, HI, HBr, HNO3, H2SO4, and HClO4. So the number of oxygens is important. We're going to talk about that in a moment on the next page. So we're left with a negative, and negatives are going to be bases. So that one would be basic or a pH above 7. All right, next one we talked about, it comes out as a base because it was amphiprotic. So we had to compare Ka and Kb. Now the last one, you can't cross anything out. So you have an acid and you have a base. Anybody want to guess how we'd have to figure this one out?
Look at the Ka and the Kb.
We need that handy dandy chart. So for the NH4, we look up its Ka, and yeah, here's our NH4. So as ammonium, NH4, so 5.6 e to negative 10. And then we have to find F as F negative, which is up here. So 1.4 e to negative 11. And that's its Kb. And the Ka is greater, so it's going to be acidic. We're not going to do math with it. We're just like finding that tipping point, which one's higher. So if this was a question, let's say on your celebration, you would have to, this is like all the work I would need to see, that you looked up the Ka, you looked up the Kb, you give them to me so I can see you looked them up, and then you would just circle the one that wins. It's acidic. I'm not asking you to solve for pH. That would be a whole nother can of worms. All right, we're going to do some math. I have a bunch of comments here. So today's study set and worksheet, we're doing x squared problem. We're doing more x squared here. The difference is we're going to do it with a salt. And sorry, typically we were in a classroom, so you had to do it with the numbers I gave you. And there's a reason, because we're going to be using these next week. NH4, the Cl doesn't matter. So you can ignore the Cl. The time you cannot is if you start with grams, you need the total compound to go to moles. And so like here, we're going to have to figure out the full compound to change the grams to moles. And then you can't cross out the sodium to go to moles. You can ponder that. All right, but here I started you with molarity. This is an acid. So that's the first step I said here. Determine if the salt is an acid or a base. It's going to be like one of these first scenarios here. You're not going to have to do a Ka, Kb thing quite yet. All right, if it's an acid, you must use Ka. If it's a base, you're going to use Kb. So the thing that happens, so in these guys are pharmaceuticals. The drugs, they're like in nature. Ionic compounds are much more stable. They also don't smell. And so most things are made as ionic compounds because they have a much longer shelf life. They're also water soluble, and we're water based, so that makes it much easier to work with. However, they don't usually usually you don't have a chart like the one that I gave you there, that usually they'll just know the Kb of NH3. There was something 2 pages ago, I gave you a little formula that we're going to be using a lot in the next 2 weeks. Is if you know the Ka, if you know one of them, you can always change the other, meaning if we know the Kb for the NH3 for the base, then the Ka times the Kb is 10 to the negative 14. We use this so much, it just is going to become second nature. So this is the base, this is the conjugate acid. It's not talking about the same, yeah, we use this a lot. Oh, I don't remember what I was going to say. So given the Kb, you don't have to do a Google search or look on the chart and look up the Ka. You can just simply convert it. And you want to get to the point where you're like, okay, the information's there. I'm just going to simply convert. And in fact, if I'm giving you the information, I'm asking you to show me that conversion. So we're going to do Ka. So we want to state our formula. Ka equals a comment that I will make to you. And this is the huge disadvantage you guys have in an online environment, that you end up deciding that you're just going to print a whole bunch of notes and a whole bunch of charts and just use that instead of using, this is the best place in the world. So my students, when we did this, they actually ended up doing amazing because we just kept using this formula. And so you just keep stating the formula every time you use it, it's just going to be there. You can have it on your notes as a backup thing, but yeah, keep it simple. All right, so 10 to the negative 14 divided by the Kb, right? If I rearrange it, that's going to give me my Ka. And then that's going to equal x squared. These are my x's over the 0.5. That was my acid down there. So we can very easily change the Kb to the Ka. This one was in the chart, but you're going to often get ones where I don't even tell you what the acid is, so you're not going to even be able to look it up online, or I make something up, so you have to use my numbers. So learn how to do that. All right, once you solve for this, you can either number your steps, or you can use the arrows that we would do the negative log of the x, and we will find the pH. And I'm okay with you stating the formula like that. So negative log of the x is going to give us our pH. And you should be able to get the 4.78. Questions? So that's all there is. These are x squared problems over the molarity. The key is this thing, that if it's an acid, that first step, is it an acid or base? If it's an acid, you have to use Ka. If it's a base, you have to use Kb. So the second question is usually how they're worded. These can, a lot of these, they always flip. As soon as you add the sodium, you took something that was an acid and now we made it into the conjugate base. So here's our propanoic acid. It tells you it's obviously a weak acid. There's our Ka value, and then we made it into the sodium salt, which means the conjugate base. So it's going back when we wrote those chemical equations a couple pages ago. The acid becomes the base. In this case, we had a base, NH3, and we changed it into the conjugate acid or the acid. All right, since this is going to be a base that we're dealing with, because that's what I'm giving you 5 grams of, we're going to have to use Kb. Before we can use Kb, though, we have to find molarity. But I'm going to show you doing it in one, well, yeah. To find molarity, right, we have, we'll break it into steps. We have 5 grams and we have 250 milliliters. This is where we have to get to moles per liter. So you're like, okay, I can do that. Well, we have to change our grams to moles. And I didn't give you a chemical compound. And you're like, oh, I'll just Google it. I've already done it. I'm 10 steps ahead of her. I'm 3 pages ahead. I'm already doing next week's stuff. Oh, there's a reason why I don't post next week's stuff. But Khan Academy does, apparently. Yeah. And tutoring does. They think it's great for them to have everything. So you can always be 10 steps ahead, and then you're actually 20 steps behind because you went too far into it. You have the capability without using Google to actually write the formula of sodium propanoate. And that's why we wrote the chemical equations. So this was our compound, CH3, CH2, CO2H. This is so fun teaching to all black boxes because I feel like I'm just talking to myself. So it's kind of like I'm in the dream. What would happen if I just decided to become a black box? You know, that's going to happen. It's like this whole Zoom thing's going to push me to that point that I'm going to be like, you know what? I'm just going to do that. I'm going to mute myself and become a black box and just walk away and nobody will know, except that I'm the one recording. I've told you a story where my internet went off and it came back on 5 minutes later and the whole class was sitting there waiting for me. It was like the Tibetan monks. I used to teach Tibetan monks to speak English. They didn't learn any English. Anyway, organic acids. You're looking at this part. This is the hydrogen that gets replaced. So it's back to the question some of you were asking me in office hours or previously, what do we do with the sodium? I don't want to just cross the sodium out. The sodium and hydrogen switch places. So if this is propanoic acid, sodium propanoate just means we cross the hydrogen out and we put the sodium on there. Now, this is just how biochemists write it because we're saying we have a carbon, we have another carbon, then we have a CO2, and then we have sodium. You can condense it down and write, okay, I have this many carbons, this many hydrogens, but our formula of this is that whatever this would be, CH3, CH2, CO2, and now it would be a sodium. The hydrogen comes off and replace it with the sodium. So you can figure out the mass of that. And then, of course, changing your milliliters to liters. And you have to be in molarity. Kb, we would state our formula. As long as you know Ka, you can do Kb. It's the exact opposite. Instead of hydronium, we write hydroxide. And by the way, several of you went and turned your cameras on. I do appreciate it. I don't know why. I know some people may have had cameras on, but it is really nice to be present. I unfortunately, when I'm teaching, can't do the multi-dimensional thing where I can see you all hiding in your black boxes. Wouldn't that be great if I could?
I thought I had mine on the whole time. I'm gonna look up and it's not even there.
Oh, really? I know. I thought it was weird when yours goes off because you always have it on. But majors shouldn't have to take one always for the whole team. All right. Yeah, so if you know Ka, you know the Kb formula. Pretend like you're really in a class. Instead of just like everything's notes and overwhelming with binders of notes and printing all these different notes, just do it. And it will be there and you'll know it. And So you'll have X squared over this molarity. To find the KB, I gave you the KA rather than having to use Google. If you're trying, and I know this because this is what happened previous 2 terms, that some students were like, I'll just use Google to find everything. You're not going to finish in the time limit that you are given. So 10 to negative 14 divided by the KA will give you the KB. And so that's what you would do. Just one more piece. Once you find X, if it's a KB, X is the hydroxide. I said this yesterday. Always state that. When you solve X, take a deep breath. Breathing is good. Regulate your pH. And state, my X is my hydronium or my X is my hydroxide. If it's a base, it's your hydroxide. When you do the negative log of the X, you're not going to get pH. You're going to get POH. And then that last step, the question, he just got kicked out. That's so funny. Is to do pH plus POH equals 14. This step, in all honesty, you don't have to show me that step. You can just do negative log of X, get me the POH, and then say what the next step is. So if my POH is this, then my pH must be that. This should become, by the time we get through Monday's class, some of these formulas should just be there that you've got it. Like the Ka formula, the pH formula, the POH formula. Right now, it's just the first day of, it's like yesterday we saw it in the notes, and of course it looked really easy because those formulas are there. And it's not because I've been teaching for 25 years. I guarantee if I went and asked my students from 10 years ago, these formulas are still there in their brain. You use pH. We use it like all of next week. And so you just want them there that you're not sorting through notes looking for them. All right, I will leave those for you to try. We got one more page to go. And this is one of these theoretical pages. So Monday's class is we're going to do a practice test together, or practice celebration together. So it's one from like many years, a couple years ago. And so I'll post that. And that's what we'll be doing during these 2 hours. If you have time to try it beforehand, you can also, what you might want to do is you can just sit back and just like make notes on it, but then you want to actually try it. And yeah, if you do it beforehand, that way if you have questions. And then next Tuesday is our first celebration. So everything up through so everything we learned this week. So the equilibrium stuff and the acid bases. So next Tuesday, anything that you have that will be late has to be in by Tuesday. All right. And by then, you guys will have made your healthy change for a whole week. So you'll be feeling really good. Right now, some people are in like their 3rd day. And so sometimes you're kind of groggy because giving up sugar, usually the 3rd day, your body's like, I want sugar. It's somewhere around the 6th day where you're like, oh man, I'm so happy. Your body, your cells are just like thanking you. They're like singing vibrational. They're probably playing the bassoon or something, saying thank you for getting rid of all that sugar. All right, polyprotic. I alluded to this earlier with the chart. Polyprotic, because they have multiple hydrogens, they actually have multiple Ka values. So this is to give up the first hydrogen. It's a lot harder. You can see almost 1,000,000 times harder to give up that next hydrogen. And then that last hydrogen, you can see that K value is really, really small. And so that's why on that one chart, it showed, this was on page 17, it showed like for some of them, it shows multiple K values. So K1, K2, K3. And that's because to give up one hydrogen and then the next hydrogen and the next one. And it always becomes progressively harder. This picture is of a titration curve. We're going to do those next week. We're not going to do the math with them because your teacher doesn't have the patience to do this. But the thing that it says here is, and I used to do the math to prove to the students this comment that there's over 1 million times more hydroniums given off from the first hydrogen. The second hydrogen is so weak, it's going pretty much backwards. There's so little given off that you would have to show the pH with like 8 sig figs to see a change in the pH. And we're not going to do 8 sig figs unless you're one of those students who likes having 8 sig figs. And then of course, to see the change of this one, we'd have to go like 12 sig figs or something. I do want to go through some of this, especially this down here. This is actually pretty important. Do you guys remember Gilbert Lewis? Those of you who just had Chem 222 with Dr. Cohen, first thing you did in 222, whoever you had, was Lewis structures. So Gilbert Lewis is a famous chemist. Other people like Linus Pauling came up with a way of drawing structures. Gilbert Lewis's was actually more elegant than Linus Pauling's, though. So Lewis structures were dealing all about electrons. So his definition of a Lewis acid is it accepts electrons. Rather than donating hydrogens, which is how protons, and his Lewis base is something that donates electrons. The classic example is nitrogen. So if we think of NH3, or however you want to do nitrogen, it has those 2 extra electrons that it wants to donate. So those lone pair of electrons, the advantage of Lewis's definition is it expanded the possibility of acids and bases beyond things that had hydrogen and hydroxide. An example of a Lewis acid is, you may remember poor old boron. Boron didn't make it ever to its octet because it would have an empty, this was empty. It always only could make it to 6 unless it got help from a friend. And that's what happens here with nitrogen. Is nitrogen's going to donate its electrons, not giving them, but it's going to donate them to the bond. And so this would be our acid. It's accepting the electrons. This would be the base. And we end up with a compound where the boron with its chlorines, the chlorines would have its dots. Sorry. And we get a bond to the nitrogen. And so that would be a Lewis acid-base reaction. All right. So you're looking either for an empty orbital or an extra pair of electrons. All right. The other 2 pieces here, these are looking at the halogens. HI is HBr and HCl, and then HF. These guys are, these first 3 are considered strong, and HF actually does have a Ka value. It is, sorry, my thing is off. It is actually considered a weak. You guys are all really nice. My one class always was like, your page is crooked. It's because I think my eyes are crooked. Yeah. The reason for that, this is actually the strongest of those 3 strong. And it has to do with the size of the iodine. So because of the size, it's the largest atom of the family, right? If you actually did the next halogen, you would get an even stronger acid, except astantine, you can't even look at it because it will burn out your eyes. So anybody who's ever tried that experiment's blind, so they haven't written about it. That's true, right? This is the one that gets the feminine name because she's so reactive. All right, so this is the largest atom, which means because it has so many orbitals, that hydrogen, which is way out there, it's really easy to pull it off. because it's so far out. It's kind of like the iodine doesn't know what's going on out there. That's the idea here. As atoms get bigger within a family, they usually become stronger acids. That's comparing within a family. This one's actually much more important, and it just has to do as you increase the number of oxygens. So sulfuric acid, H2SO4, is a strong acid. The more oxygens, you get more pooling. So as you increase, it's right over here, as you increase the number of oxygens, you increase the pool or the polarity. And so acid strength has to do with how easy, if you think about this, acid strength has to do with how easy to donate or pull off the how easy to pull off the hydrogen. So a stronger acid, it's going to be really easy to pull off the hydrogen. So you're going to have more hydrogen there. So something that has more oxygens, the oxygens, remember, are really greedy. So the oxygens are pulling. So because they're pulling more, higher polarity, that bond is extremely polar. So it increases the polarity of the bond, and it's easier to remove the hydrogen. So you increase the acidity. So H2SO4 would definitely be a stronger acid. I mentioned this when I talked about the organic acids. So they need that double oxygen on the carbon, and that creates that strong pool that allows the hydrogen to be pulled off to be by something else. All right, this last one is actually a question. We've actually already done it, and you will definitely see it again. It's on the study set for Monday, and it will be on the review. It will be on the exam, and so it's a mini chart, as I promised. We just have 3 acids that are given. I want to mention something about the middle acid. So Hockel. So that's how they write it. Most people write it. It is also, when you learned it in first term Gen Chem, we probably always writing as HClO. It's the same thing. So the hydrogen is attached to the oxygen. They're the same thing. So don't let that confuse you if you see it one way somewhere else. All right, we're comparing Ka values. So you're going to see this a bit on you've seen it on the worksheets where I ask you to explain, or you can. Some of you I've found like to write long paragraph explanations. But which one's going to have the lowest pH? Anybody?
HNO2.
There we go. I knew somebody had to be there. Yes. HNO2. Why?
It's the strongest acid.
Yeah, the higher the Ka, the stronger the acid. Sorry, I meant to say strength, so stronger acid. And this goes back to something I talked about yesterday. The stronger the acid, the lower the pH. Yeah. All right. So comparing these Kas, this one's our strongest. All right. Which one is going to have the strongest conjugate base?
The HOCl, because it has the, oh wait, never mind, the HCN.
Yes. Because the lower the Ka.
Ka is the lowest.
Yeah, lower Ka means higher Kb. So stronger the acid, the weaker the acid, sorry. The weaker the acid, the stronger the conjugate base. So as Ka goes up, the Kb of its complement goes. They always go opposite. All right, so one more. So from what we've done, and is actually a question that's on the today's study set, but I give you a hint. That little p means negative log. And so this would be negative log of the Ka. You don't have to put a parentheses, but I did there. So from what we've seen about if something has a stronger acid, which means more hydroniums given off, something I talked about yesterday, the stronger the acid, the lower the pH. The more hydronium, the lower the pH. They're always opposite. So pKa, so the lowest pKa will mean which Ka are we going to pick? We're going to be opposite. The higher the Ka, the lower the pKa. It has to do with that negative sign. So they always go opposite directions. So same with hydroxide. The lower the POH, the higher the hydroxide. So which one had the highest Ka was the HNO2. And yeah, some people like to use pKas. There's some formulas where they do everything. We get to buffers, and I'll talk about that. And some students really don't like pKas. Ideally, if you understand this idea of the relationship, either way should work for you. Questions? So, x squared. Kas and Kbs right now, they're x squared. That holds true through Tuesday. So just keep them as x squared, and we'll worry about what happens on Wednesday after Tuesday. In fact, let's worry about today. And so what do you guys have due today is you have a study set due by 6 o'clock. And actually, you guys have an advantage since you were here. The study set, you should be able to make a decent go at it. The first page of the study says more theoretical stuff, so try it. Try something. Don't like leave lots of blanks. And then the second page is a lot of the x squared problems. And I will hang out for like an hour if you want to work on them. The worksheet is due by midnight, and it's probably the easiest worksheet you're going to have. So some people did the worksheet first. It's probably easier in the study set. And then I will open the folder for next week. Tomorrow, you have a lab due. So the Le Chatelier's lab, you just watch the video and answer the questions along with me. And you can do it today. I'll have office hours at 5, or you can come tomorrow and if you want me to look it over, but it's pretty straightforward. All right, I'm going to stop. Oh, and next week is our celebration and famous chemist. Stop.